All right. Well, as we're started, Mike's camping. The sun is setting,
Yeah,
and
yeah.
we have Sky with us. It was Phil presenting, or does Sky want to go, or how
Sky,
should we?
yeah, yeah, me. Um, Nice to be on here. Does this screen sharing work? Okay.
This one or
Yep.
the other one? That one?
Yeah, this is the right one. Yeah.
Great.
So
All yours.
this is, by the way, this is a painting about my theory. It's German Elementarräume. It means elementary spaces. Those are the space quanta of my theory, as they should exist in any theory of quantum gravity. So I started this theory in 2003, but the main part is actually 2005. Um, this is dealing with, at the beginning, just with quantum mechanics, what is a superposition? And so the idea was that it's not the particles that are fuzzy, but it's us. We are in all the worlds that are indistinguishable to us at the moment. So we don't know if this particle is here or there before we measure. So it's in both places at once. So basically, I took the phase space where every point represents the state of the universe in one moment, and I extended it into a cloud because it cannot be a point. There's uncertainty, so it's like a cloud. Um, Many people say that the Copenhagen interpretation, which says that consciousness is central, that it could lead to solipsism because I have to observe you in order to exist, and you have to observe me. And it's kind of hard to figure out how that can work, especially when you operate in space-time where the speed of light is limited. And the way to solve this problem is basically by using entanglement. We are all entangled with each other, so we share one collective wave function, and that's updated in a collective way. So it represents the knowledge of all of the collective of observers, not just one observer. Um, and this basically means that we here on Earth, we are in an island of entanglement, and everything outside is basically a superposition and kind of not really there. Like it's there when you go there, but you're just seeing a potential existence there. You're just seeing the sun as it was 8 minutes ago, and you don't know how it is right now. And this explains the cosmic microwave anomalies. I don't know if anyone have heard of them. They were a big thing starting 2004, and then 2014 that they sent out the Planck satellite to check if they're really there or they're kind of from background contamination from Earth's atmosphere. And everyone was shocked that they were still there, but then it became uncomfortable to talk about it. And the one who discovered them, Max Tegmark, discovered like the quadrupole, that there are cold spots basically in the direction of the north and south pole of Earth and the north and south pole of the orbit of Earth around the sun. He basically more or less left cosmology, or mostly focusing on AI stuff right now at the moment. So I think that was kind of an uncomfortable truth, and also like a 180 reversal from what he published in his books before. Um, yeah, this is not like the main topic of my talk, so I'm just going over those points quickly. So when you explain quantum mechanics by saying we are in all worlds that are indistinguishable at the moment, you can it's kind of a simple explanation, and it solves the problem how you can have entanglement. Basically, in each world, like it was on the slide before, in each world you see that the spins are orthogonal. So when you measure, it's not strange to find them being orthogonal. So there's no spooky thing going on. Actually, it's all very natural. So, but anyway, this explanation is too simple because this way you can only explain a probability distribution that is like shaped like a mountain, but you need something wave-like. You can have that if you have space quanta, which are like spheres, And there's this idea, this analogy between black holes and elementary particles. But what you need is something that is a little bit like a black hole, like something that's proportional to mass, or mass energy, actually, energy. And so it's bigger when the energy is bigger. And so you can have a sea of overlapping spheres, and you can construct a space out of that. And that has to be complex number surface, and that oscillates. Like a complex number goes around the complex plane, the origin of the complex plane, and so it phases in and out of existence. So the real part of every space quanta is shrinking down to zero and then expanding again. And that does the following. It basically makes the probability to detect a particle among every pathway go up and down like a wave. So here, the probability might be zero when you measure here when it has reached zero, but on another pathway, it might not be zero. So that's how you can get a probability distribution. But something that I hadn't realized quite in the early days, and I had realized it a bit, but I didn't try to find ways to test it experimentally, is that this actually means that the Born rule is changed. This is the normal Born rule. You take the square of the complex number to get the probability. But here you take the square of the real component of this complex amplitude and double that, and that's your probabilities. That's quite different. And when you look into lasers, you look into them, you see this granular structure, which actually, when you look at them with your bare eye, it changes a lot because you move left and right. But when you use a camera that is stationary, you see that those granular structures are very, very stable. And basically, those are the spots where the wave function goes to, the real component of the wave function goes to zero, which in standard quantum mechanics doesn't happen. It's always, the absolute value is always the same. Yes, the complex number changes, but the absolute value is always the same. Okay, so next topic again. So this is all one overarching theory of quantum gravity, and quantum gravity is supposed to solve all problems. So it has to deal with all topics that exist in physics, basically.
Right? A unified theory. That's the only way. It's got to take everything on. I feel that.
Yeah, thank you. So there will be a lot of topics. I'm trying to focus on gravity, but so I will try to go quickly through these topics. Entropic expansion is basically, I agree with Newton that Newton was asked, if there's universal gravity, then why doesn't everything just collapse? And he said, well, if the universe is infinite, then there's no center of gravity, and then you cannot have the universe collapsing. And that's just such a simple logic. I just can't believe how Einstein could just disregard this logic, and all those people who came after him, like Friedman, they're all using math, which is basically just taking the Einstein field equation, which is only made for one object. You cannot even use it applied on two objects. And they just take it, which is basically they take the equation of collapsing star becoming a black hole, just take that upside down and then pretend it's an expanding universe. And then you get the absurd result that the probability for the universe to be as flat as we observed, spatially flat, no spatial curvature, the probability of that would be 1 in 10 to the power of 62. So that's the flatness problem. And instead of taking that as disproving Einstein's theory, at least when it comes to the cosmology, in my opinion, it doesn't say anything about cosmology. Instead of taking that as a disproof, they just invent inflation theory and try to solve it. So instead of, when a theory is disproven, instead of accepting that, they just invent some new stuff like dark matter, dark energy, inflation, all this kind of stuff. What I do here is I accept that it cannot collapse, and then I ask, okay, so why is it expanding? Like when you think it can collapse, then you can just think, oh, maybe it can't bounce back or something like that. So why is it expanding? So I'm saying it's expanding because of entropy, and it's in particular the entropy of black holes. So at the beginning, I didn't quite realize, okay, the entropy is actually a quadratic function. If you feed the black hole linearly, it grows like a quadratic function. At the beginning, I was thinking, oh, maybe the black holes are growing faster or something. And I look, okay, they were quasars first. But then I realized, oh, wait a moment, the surface, the entropy depends on the surface area, so it's a quadratic function. So if the expansion of the universe is in order to keep the entropy density constant, then it make then if it depends on entropy, entropy is like a quadratic function, so that makes sense. And it's all already kind of in Penrose's book. You see the how he describes how the entropy changes, and he kind of alludes that it's constant in the middle, but then he still believes in Big Bang theory and all of that stuff. So he doesn't take his own diagram seriously. If he would stare into it and like meditate on it, maybe he would have this idea. But it's unlikely because he's very keen on Einstein's theory being the correct one and there being something wrong with quantum theory rather. Okay, then something not so important, but mathematically kind of impressive a little bit. I solved the hierarchy problem, like calculating how much of these vacuum fluctuations are there already in empty space. And the more you have of them, the weaker is gravity, because gravity basically depends on where there are more space quanta. So if you have a lot of space quanta here, then things are attracted to that place. So all of space is made of these vacuum fluctuations, and so every particle has a lot of gauge bosons coming out of it. So that increases the density of space quanta here. So everything gets attracted to it geometrically. So it's still, I'm not using curved space, but I'm using granular space. But it's still similar to Einstein's theory in that regard, because you have, instead of curvature, you have different densities of space. And if you already have an awful amount, crazy amount of these space quanta here, and you add one particle there, one charge, I guess you like the idea that charge is the thing that is important, not mass. So you have one charge here or one hypercharge, and in my theory it turns out that hypercharges are more important. It doesn't do all that much because you already have this huge sea of virtual particles. And so that explains why gravity is so incredibly weak. Okay, now here again, back to cosmology. I checked it predicts, this theory predicts that the universe started off very slow and then became faster and faster, like a quadratic function. And it predicts that the true age of the universe is 42 trillion years. And I tested that by looking at all the supernova that exists. And it shows that the luminosity decreases with the square of the distance, as one would think, if the distances are correct, but in Einstein's theory they're not correct. So on the left side you see my theory, on the right side you see Einstein's theory. You see my theory matches, his theory doesn't match. But in general relativity, it will match for distances for redshift smaller than 0.2. That's because in Einstein's theory, basically, they're using two different formula for redshift smaller than 0.2 and another one for bigger. So this analysis basically shows that it can only be one equation, cannot be two equations. In Einstein's theory, actually, it's many more equations if you go to even higher redshifts, which haven't been observed yet because they're too far away, except of course for the cosmic microwave background, which is the maximal redshift. So this analysis only shows that it cannot be two equations, has to be one. But a way of furthermore confirming my distances is to look at the average luminosity of supernova, and that's, in my theory, it's very close to the predicted, theoretically expected value, whereas in Einstein's theory, it's not. And it's actually well known, people know that, or at least some people know, that there's huge problems with supernovae. They're too faint, the very distant supernovae are too faint for the distance they're supposed to be. And people have resolved that problem a little bit with dark energy, making the universe go faster. And I agree with that part, but the way they're doing it is not really solving the problem. It's just making the problem a bit smaller. But since 2019, there's this Hubble tension, and it's even all over the newspaper saying that cosmology doesn't add up. And physicists I talk to, other physicists, they basically say they left cosmology, or they're not interested in cosmology anymore because it's such a mess. Okay. Yeah, sorry to jump between topics so much. Um, um, Quantum eraser experiments. They basically, you can use a quantum eraser experiment to prove that actually it's consciousness that collapsed the wave function. You can do that by erasing the. Uh-huh. You can do that by erasing the which path information after the screen has been, the detector screen has been hit. And then the erasing is still possible, which proves that it's not the screen collapsing the wave function. And then you can even use that. You can look how long you can delay the erasing of the which path information, and then you can figure out when exactly the wave function collapsed. That's how you can, and I published that also as a paper in 2018. So, but it's very hard to delay it by a lot of time because light is so fast. You would have to slow it down somehow using a Bose-Einstein condensate. Yeah, so here now I have to explain how Einstein's the things that are confirmed within Einstein's theory, how they work, because there are things you cannot deny, like time dilation. So basically, the way you get speed-dependent time dilation in SPD quantum gravity is you say, okay, when the size of particles of space quanta depends on the energy. So if you have a spaceship and all this space quanta in the spaceship are inflated, inside the spaceship you will not notice it, but it will manifest. It's like changing constants. If you make the space quanta bigger, I mean, they have a bunch of constants in the formula for space quanta radius. There's the speed of light and everything. And if you change any of the constants, g, well, g is not really a constant, but okay, you could, we'll come to that later, that g is not a constant. But you can change any of the fundamental constants like c or h and so on. Well, it's 3 of them. And it will always result in time dilation. So that's how you can explain time dilation dependent on speed. And dependent on gravity, basically what you do is you're here on Earth, and you have how weak gravity is depends on how much quantum vacuum, how many of these space bubbles are there. And on Earth, you have the background from the quantum vacuum plus the background from all the gauge bosons that are streaming out of Earth, because there are a lot of charges and hypercharges inside Earth, all the particles that make up Earth. So on Earth, gravity is weaker than in outer space. But you can't notice it because it's uniformly weaker. Like in your frame of reference, it's weaker everywhere. So that's like changing constant. So that results in time dilation again. And it's important to notice that there's a maximal time dilation for gravity. If the escape velocity becomes the speed of light, like for a black hole, that's where you'll reach the limit. You can never go beyond that. That's why a star can never collapse further than the Schwarzschild radius. It can never actually become a true black hole. It will always be right before becoming that. So it's a star frozen in time. So you could also call it an eternally collapsing object. Yeah. By the way, I'm looking at my PPT, so I'm not seeing you here. Cannot look at both at the same time. Hope that doesn't matter. Okay, so that's what I said just now in the last slide. Yeah. Particles can come infinitely close to the speed of light, but they can never reach it. Escape velocities can come infinitely close to the speed of light, but they can never reach it. Hawking radiation doesn't exist because if you have gravity depending on the number of charges or hypercharges, then, well, photons don't have hypercharges or charges. They're just photons. They don't have, they don't consist of quarks or protons, neutrons. So a photon cannot carry away gravity. That's why black holes cannot evaporate. And I mean, if black holes could evaporate, that would violate baryon number conservation, lepton number conservation, because you have everything turned into light. Also, the second law of thermodynamics is violated. Well, people would try to convince you that the second law of thermodynamics is not violated by saying, well, the Hawking radiation goes into random directions, but that doesn't really help, because if it becomes a sea of photons, you can measure those photons and you know where they are and what their color is and everything, the frequency. So that's not like a black hole where you cannot see inside. So the entropy certainly would certainly be violated. The second law of thermodynamics would certainly be violated. But people only focus on information conservation, only 1 point out of 4. Okay, so now let's get to the gravity part of it, which is the main part. Now I already lost a half hour talking about the other parts, but all the rest now will be gravity. So here's the main calculation that you need. You want to, if gravity only depends on the number of particles, on the number of protons and neutrons, and this is something that should be interesting also due to electric universe people, which I'm not one of them, but depending on the intricacies of the theory.
I see the same slide.
Yeah, do you need me to switch to this one with the different slides?
Wait a moment, I was talking and I was switching slides all the time. You were not switching, it was not switching here?
No, it was not switching under this one.
So my whole talk is wasted then.
We were following for the most part. We just didn't have the slides. So
out of the slides, so how can I switch this? I was switching my own slides here. I thought you were seeing that. I thought it's a screen share.
It
It's not a
is,
screen
but
share.
it's just showing the first one consistently.
Oh no, that's terrible.
Maybe try this one. Are
but
these the slides?
I'm sharing the screen. Okay, so only you can switch the slides.
I think you should be able to. Are these the slides though?
Okay, yeah, I'm able to switch the slides. Yeah, but we are half hour in and now. Okay, let's just go through it
That's
quickly.
okay. Don't worry about it. It happens. You just kind of go over some of the stuff,
Okay, okay. Just quickly here you see the picture of the spins.
Sky, there's no time limit, so just take your time and tell us what you want to tell. No pressure.
Okay, I will just go through the pictures so that you have seen the pictures. Here you see the spins that are orthogonal on each of the indistinguishable worlds. Here you see the phase space, how we turn a point in phase space into a cloud. Okay, next one. Here you see the no alien prediction, basically that we are all connected through entanglement. And yeah, that's that. And then here you can see the quadrupole, that there's those cold spots that Max Tegmark discovered, and they are aligned with the equinox and ecliptic of Earth. So here you can see concentric circles here, but they're actually a bit more explained by south asymmetry, so that's connected to that straight line. It looks like, and so it's not really straight. And when you have more space quanta here, you see it's only the real component of the complex number, so it turns to zero, the probability every time the real component is reaching zero. Here you can see the entropic expansion. You can see how the black holes grow and then the density goes down. So that's why the universe is expanding, and it's expanding like a quadratic function. It's not like in the mainstream where it's starting off 17 times faster than now, then slowing down, and then speeding up again. It's very complicated in the mainstream, and the data just doesn't show that kind of complication. Here again, the hierarchy problem. Yeah, there's nothing much to see. I already explained it. And here you can see the data. You can see here how the inverse square law of luminosity. So here you can see it goes up. Luminosity actually goes down, but this is the magnitude, and magnitude is an inverse square logarithmic measure for luminosity. That's why it goes up instead of down. Here's the quantum eraser experiment. You can delay it more and more to see how when the wave function actually collapses. Here, yes, this is time dilation. Just some illustration here. I already explained this. Yeah, meme about it. Yeah, Hawking radiation. Okay, now we get to the gist, the gravity part. So if gravity depends on the number of particles, which actually should also be the case in all those theories, electric universe theories, which mostly are not very mathematical, and I don't really agree with them, but they should expect some similar results depending on how they count the neutron. Some electric universe proponents, they deny quarks, but then they would have to count the neutron as 0. So that wouldn't work. It wouldn't be supported by the data. But if they use quarks, then they could use an electric universe theory and still get close to the pretty close to the actual data in the experiments. So if you want to cut, you have the gravitational constant of iron, and the official gravitational constant was measured with stainless steel, which is close to iron. You take that number, and which for stainless steel is actually not 6.6743, but 6.6742 if you use stainless steel. So then you take that number and you can extrapolate how the gravitational constant should be for hydrogen, which doesn't have all the binding energy. So binding energy does the following. It is negative energy, and because mass equals energy, it reduces the mass, but it doesn't reduce the number of particles. So you have more particles per kilogram mass or per gram mass. So, but for hydrogen, it's not like that. There's no binding energy, so you don't have so much gravity per kilogram. It's because the mass is not reduced for hydrogen. So you can calculate out the all this binding energy and get the gravitational constant for hydrogen. What you do here, I don't know if you see in my mouse. Can you see my mouse in the screen share?
No, it's because it's preloaded.
Okay, yeah,
Slides
it's
that
preloaded.
indicate.
Okay, so with mouse it would be better, but it doesn't matter. Okay, so you can see iron inertial mass. You just take the atomic mass of all the different isotopes, and you multiply them with the percentages. How many percent of this isotope? How many percent of that isotope? So in this case, it's iron. So we're calculating out all the binding energy for iron. So then we get the sum for the inertial mass. That's basically the mass that everybody knows about. Gravitational mass, nobody knows about it. Gravitational mass is what you would get if you just naively add up all the protons and neutrons together and look at the result. So I did that, but for the isotopes, you have 26 protons, 28 neutrons, then 30 neutrons, 31 neutrons, 32 neutrons. So that's the result you get. And then you divide the top by the bottom one, the inertial mass through the gravitational mass. And well, gravitational mass is just a name; it's not really a mass. But in this context, it makes sense to write it down like that. And you multiply that with the that ratio with the gravitational constant of iron, and then you get the gravitational constant of hydrogen. So that you can use as a basis to calculate the gravitational constant of all elements. So the next, where do I click here? The next slide. So here you have lead, and just now I also did an experiment, free fall experiment with lead. So here you just divide the opposite way around. You divide the bottom number by the top number and multiply that with the gravitational constant of hydrogen. So then you get back up again. You calculate how it looks like when you go to the bottom to hydrogen, and then you calculate how you get back up to some other element. And then for molecules, you need to be careful how you're doing it. You shouldn't mess it up. So you should, for the inertial mass, you have to separately, you 2 times hydrogen and then 1 time oxygen. Has to be clean. You shouldn't be using some average or something. Average would be wrong. It has to be this kind of sum. You shouldn't be using some average G values. Like at the beginning, I was doing it like that, and that's totally wrong. So this is a mixed materials. You don't need to look at the numbers. You just need to know the percentages need to be atomic mass, atomic percentages, not mass percentages. You need to know how many percent this atom, how many percent that atom, not by mass, because some atoms are very heavy, so they will be a very tiny mass percentage, but maybe a very big percentage in terms of atoms. Okay, now this is the most important part of the whole talk. These are all the experiments that exist, all the measurements of the gravitational constant over the last 50 years. So you would think it would be better to include the last 200 years, but actually no, because the initial experiments were not precise enough. They were very messy. So they're good enough. The experiments are good enough since about 1969. Experiments done by Rose and Taylor and some others. So those are the good experiments, and then you can see also here Hale did experiments that were before that time, but they were already good. So that's the only exception. His experiments were good, and he was the one of the only ones who did different materials at the same time. And he was perplexed because he was getting different numbers. So then instead of just believing that, he went back and he did the adverse experiments with Einstein cited for his equivalence principle. And because of the design of that experiment, it's designed in a way that makes these differences almost infinitely small. Like instead of a thousandth, it becomes like a millionth or something. But that's at the end of the talk, that part. So he just disregarded that then later, and then he just used one material. And the same happened to Ponticus from France in 1971. He used different materials. But he didn't do that Edwish experiment to convince him. He was already. It was what he did is he just took all the numbers, ran them through a computer, and they did some data homogenization that they do in climate chunk science a lot. Yeah, then he just got equal numbers or similar numbers. So that's kind of fraud, I would say. And then he just left physics altogether and went into climate science, where this kind of behavior is sort of more acceptable. And then in recent years, they have all been using stainless steel because that allows them to agree with each other more. Yeah. So something that I didn't do before last year is I was only looking at the source mass, not the test mass. And that way I only had very few materials, like 10 different materials. And the statistical significance was not that great. But then when I realized, okay, it was a big thinking mistake to not use both the source and the test mass. But then yeah. So it has to be the geometric mean between the source mass and the test mass. And so when you add all these experiments together, then the chance that this is a coincidence is 1 in 10 to the power of 13. Now, in my other presentations for APAC, I claimed some crazily bigger number, like or smaller number, depends on how you look at it. This is the correct one. The other one was wrong. But I had to figure out how to calculate the hierarchy, how the chances to observe such a hierarchy by coincidence, and it was not easy to calculate. I had to figure out how to calculate that. This information was not available anywhere, and still haven't seen it anywhere. But my method should be correct. Okay, next slide. I did some. Okay, one more thing I need to say about the last slide. So this is all assuming that the mass has been measured. The masses have been measured using a true balance, a mechanical balance, and all the legit experiments must have been using a mechanical balance, and they are very precise ones. I mean, in the old days, they produced a lot of mechanical balances that had could measure 4 digits after the decimal point in gram, and I bought one of those over there, but it's kind of it's broken. All those old bands are broken, and then I have a newer one here. It measures 3 digits after the decimal, 2 or 3. So yeah, they have been using mechanical balance. In my own Cavendish experiment, I was not using that, and I was not really measuring precise enough to really use that value for anything. But I did a good effort, and I did better than all the YouTube videos on YouTube where people try to do the Cavendish experiments and they all fail. Like they don't isolate for air enough. There was a teacher trying to do the experiment for 2 or 3 years, and he never isolated from air, so it always failed. And at the end, he had to give up. So basically, I put it into a big container and put glass over it. And even then, I got 1 order of magnitude too big of a big G value. And then I figured out, okay, I have to put the tape around it better. I have to fold it over before I put the tape, and I didn't know I have to fold it over. I didn't know it was that sensitive. Then I had to move it out temporarily because I was doing it in a factory, and they had to use the space as a family factory. And then outside it, I realized, okay, it's totally not isolated from air. So once I folded over, it was working well. But still, I rely on the measurements that are already out there, not on my own. So this was fun, but I'm not relying on it. And then I also did before that, I did some Bernoulli trials, which was not air isolated, but just looking at statistically, if you have iron and water, for which one will it be quicker? And I don't know if it was magnetism or a little bit of psychokinesis or what, but I was measuring the mass using a normal electrical balance, and that's just dependent on gravity. So that's not very usable here. Yeah. Differences in free fall. So it's not obvious that free fall acceleration should then also be different, but it's obvious when you look at the Newtonian equation. Where's the Newtonian version? Do I have put it here too? No, it doesn't seem so. But anyway, so you look at the first equation here. Instead of big mass multiplied by small mass, I have big Y multiplied by small y. And that's the quark count. But you can replace it by baryon count, proton-neutron count. Doesn't matter. Then this constant will be a different constant, but that's not the main point here. The point is that when you try to calculate free fall acceleration, you move over the mass here, you put it down there, and in Newton's theory, the small mass would cancel out because there would be the small mass on the numerator and the denominator, the numerator and the denominator. So then they would cancel out, but here they don't cancel out. So you get a fixed ratio between this y and this m, and that fixed ratio tells you that for every chemical composition you have a different free fall acceleration. And the more let me check on my screen because it's so small here. Yeah, okay. So I don't know if you can see this well, but the second line here, it's in white, so it's not so easily visible. You can see here it's formulated only using mass. You have the big mass, a small mass, but you have these G values that are different for each element. So so here you can let the small m cancel out. It's no problem because the chem composition of the small m, it's still here represented in the G value of the small m. So it's kind of convenient. You can let mass cancel out. Doesn't matter. It's still there, and the chemical composition is still maintained. And so this second formula is the practical one that we use in everyday life in calculations and predictions. The first one, you cannot directly observe the quark count, so it's more for the theoretical work, not so much for the practical. Yeah. So then there's the SAS drop tower experiment. There's also video of that available. You can see it in on the website of SAS, but he died. He passed away 2 years ago, and his website went down just a few days ago. I think, I don't know if it's back up, if it's a glitch. His son is managing his website. He did a free fall experiment in the Bremen drop tower, and it totally disproved Einstein's theory. But well, they only let him drop it one time because they didn't like his conclusion at all. They were horrified by his conclusion, so they didn't let him try again. And then he even went in front of the courts, and he became very bitter. His whole website was ranting against the establishment, basically, for not letting him try to do it again. And the way they let him do it was also not so perfect, because they only let people drop things inside their aluminum container, and then they stick to the ground. And especially when you make a vacuum, then something can get stuck on the ground. Really, this is like a vacuum welding. And actually, two masses got stuck on the ground, beryllium and boron. So that's why the experiment is not perfect. Only aluminum and iron should have stuck to the ground, and they did stuck to the ground, because they've aluminum falls as fast as the aluminum container, and iron falls even faster, so it sticks to the ground. But you can still do some analysis of the experiment. How far did they move up, and so on. But it's just one single drop, and you cannot have standard deviations, and it's not really very scientific when you have only one single trial, and to use that is not very legit. And the p-value is not very impressive. It's just 1 in 30 chance that it's a coincidence. But while you have to take this p-value with a grain of salt, because I mean, they shouldn't have lifted off the ground at all. So you could say maybe it was shaky, and that's why they got a nudge and they moved up. But it's disproven by the fact that carbon actually got stuck for a moment and then lifted off the ground in mid-air, where nothing can hit this capsule. Okay. Next slide. This is much more impressive, but sorry, there's no picture here, and it's not something that you can have a picture of. I guess you can have a picture of the experimental apparatus, but this is a these are neutrino freefall interferometer experiments, and I don't know, is it every single one of them? But yeah, pretty much every one of them has neutrons falling slower than other objects, and that's exactly what my theory predicts. 1% slower. And on average, that's exactly what happens. It's exactly 1% slower. And yeah, neutrinos fall the slowest of all things that exist in the world. Neutrinos have the least gravity per kilogram. They're a little bit heavier than protons, so that's why the gravity per kilogram is the smallest. And these are my own free fall experiments back then, and was using this. Where is it? Using this thing here. Yeah, this was a release clamp. For that, you can only use elements that are.
Do you want to mind showing it again, Sky? Sorry, I just got you on large.
This one here from Pasco. You just put it in here, and the balls have to be electrically conductive. So I could use iron, and lead is also still fine. Lead is a little bit conductive, but most other materials I couldn't use. And it's with the receptor platform, so the values can only be too large, not too small, because there can be a delay in the release, a tinier delay. That's why for those experiments you have to actually use the minimal delay, the minimal free fall time, not the average. You cannot use the average in this case, which makes it less scientific because people like to use the average. So that's just the first version of the experiment that was back in Greece. And yeah, the predicted difference at that height, it was like very, very tiny. For 2 meters, it's 0.3 milliseconds, like 0.0003 seconds. Then later I switched to using photogates, using lasers, but still with that clamp. And that's much better. You get very much smaller. Well, the standard deviations don't change that much, but it's more scientific. And also the receptor platform doesn't always react, but the lasers, they always react. unless you miss them, then you have to readjust the position. Then later I used the magnetic release mechanism with the receptor platform. That was nice. It's a very clean release, so that makes the standard deviations much, much smaller. But then there's a downside to that. Then the size of the washers that you use for the magnet are become very important. So you use vending machine balls, and then you put the material like iron and lead, you put them inside, close it again. And the mistake that I was doing back then is to have different balls, one filled with one material, one filled with the other, the right way. And it was nice because I could alternate between them, one time this material, then the other, between each trial. And the mistake in that is because the washer size is slightly different, so that can introduce a bias. So the right way to do it is to use only one ball and then to just swap the inside. The reason I was not doing that or didn't even think about that is because at that time my vending machine balls were breaking open all the time, and I had to actually glue them to keep them closed. And now what I'm doing is I have a lot of pillows, a lot of towels. Actually, I put there like 10 different ones. Yeah, so it's very soft, and it doesn't even jump up at all, and they cannot break. And also it cannot hit the photo gate. It was hitting the photo gate all the time and was switching its position, making everything messy. Now nothing is messy. Not nothing, but these problems have been solved. So there was a bit of bias there. Then sometimes I would wrap them in paper because I didn't want laser light to pass through, because then the laser light, the laser cover time, if you measure speed, for example, then the cover time is very important because you're passing only through one laser. And if it's filled only a little bit, then it will become transparent very quickly. And then the cover time is different, changing your assessment of the speed. But if you have two laser gates, it passes through the first one and the second one. So it counts the time from when the first laser got uncovered, when the first laser got covered, and then when the second laser got covered. But then it really doesn't matter when the uncovering is. When you look at only the time between coverings or uncoverings, then it doesn't matter that it's transparent. And I also, through trial and error, I also found that it really doesn't matter. So for some time I was wrapping them in paper and tape, but I abolished that later because it didn't seem to be important. Only it's important if you want to double check the initial velocity, for example, to see if there's any repulsion from the magnetic release mechanism. But that doesn't play a role anymore when you use the same ball for both. Then you have the same washer for both, and you don't have to worry that the washer size is a little bit different. Yeah, with zinc trials, yeah, 0.5 milliseconds. Okay. Yeah, now we go to pendulum experiments. I didn't conduct them. Giorgio Toro did. He's an American who moved to Italy, and yeah, he has this Italian name. So he did this pendulum experiments in a real vacuum. And actually, my free fall experiments, they would also be better in a real vacuum, and I plan to do that because, I mean, there's so many factors. Elasticity even could play a role. The inside, the whole dynamics. So vacuum is much better. So he did them in a vacuum, and the first experiment for 2023 got the perfect hierarchy. All of the 4 elements that he used lined up perfectly, exactly as I predicted. So the chance for that is 1 divided by n factorial, so 4 factorial, so it's 24. So it's 1 in 24 chance that this is a coincidence. If you just look at the hierarchy, so here you can see easily how hierarchy works. When the hierarchy is perfect, it's very easy to calculate what the chances for the hierarchy. Just 1 in the number of configurations that you have. If you have 4 elements, it's 24. If the hierarchy is not perfect, then it gets very complicated. And it took me some time of I was thinking very deeply about this mathematics for 3 days until I figured it out. Okay, but I don't show it in this presentation. It's in the papers. In the paper. So he did this experiment again with more elements. The hierarchy was not quite perfect, almost perfect. One element was out of line, but still, if you combine the two, you get very low chance that is a coincidence. What is it here? 1 in 1,791. My turn off my background sound. Well, I have this mic, should be good enough, unless it's not well connected. If it's not well connected, I cannot do anything about it. It's too late, I guess. Or should I check the mic? No. Yeah, I should be using the right microphone. Okay, anyway.
Yeah,
Well,
we hear you just fine.
okay, so balanced scale experiments, they have been quite a ride. In the old days, actually not so long ago, I was really believing this myth that they are electronic balances because they have the name balance in the name, have balance in the name. So the reason why they call them balances is because they have this force restoration mechanism that basically looks at how much force you need to do to level out the scale. It's really just a scale. It's not a balance. So in a real balance, you have gravity actually providing that balance in force. But if you don't have that, then it really doesn't know how much electricity it needs to apply. So so you really need to use a mechanical balance, and you can look at anywhere an electronic balance. It's really just more precise. That's why they call it balance. It's not really a balance, and you still need to calibrate it for different elevations, for different local gravities. So that's not something you have to do for a real balance, a mechanical balance. And yeah, there are very precise mechanical balance, but they're not so much available in the private sector. So my early experiments on that, they were not good. I was just for the very small. If you have these element cubes, I have all these different elements, 50 different chemical elements here. You can buy them at luciteria.com. Basically, when you have a very small mass, then you measure a couple of times, and and the value can pretty much land anywhere if you compare the reading of a scale and a balance. Well, what I had back then, it was not really a scale of a balance. It was both a scale and a scale, a cheap one and an expensive one. So it was not the real deal. And the real deal I'm only doing since one day, so there are not many results. I posted one quick result yesterday on Facebook, but it's not ready yet, so I'm not going to talk much about that. But that's for the technology to build a material analyzer for you can use gravity to analyze the material. You can basically, in China sometimes they sell fake gold bars, and there's just some other metal inside, and only on the surface there's gold. So if you use a machine for material analysis, that's not it. Just to demonstrate. So they just can measure the light from the surface. So then they will think, okay, it's real gold. And if the weight is right, they can easily fake the weight by using other materials, achieve the same weight or mass. So yeah, that's something you could solve with this technology. And initially I thought I need a gravimeter to measure force very precisely. I didn't know that a normal analytical balance is already measuring force very precisely. I thought that just because it's using this force restoration mechanism, that it's not measuring force, that it's measuring mass, but no, it's measuring force. To measure mass, you really need to have this mechanical device, which is kind of cool because we moved so far away from mechanical things. Yeah. Yeah, so this is an example for classical, which actually has the right accuracy for my application, but it's broken, and they sell many of these online, but they're all broken. There was one which was not broken. It's actually the one in the picture, but I wanted to buy it, and I paid for it, but then the one trying to sell it to me, he slipped up in the stairway, and it just fell down and got broken. So that's that. And okay, here we go to some science fiction part, which is not fiction, but it's very difficult. So I guess it's a little bit of fiction there. So if you were able to inflate mass, and uh, some people they can do that, I think they can do that by just heating something up, or flying mechanics. That's crazy. You cannot do that, because E equals mc squared. You just need so much energy to change mass significantly for it to be measurable. You can see it for particles, but for big objects, nobody can do that. So one would have to be able to do that to manipulate gravity on a large scale. You could use fiber wires and fill them with some very dense gas like xenon gas, and accelerate them using lasers. But you cannot just use the laser to push it. You have to actually use a laser pulse. You have to pulse it, and you have to do it in a very sophisticated way. And people have done that with air, but of course air is not heavy enough. And your laser have to be lighter than the whole thing. You need to actually make the gas inside heavier than the whole thing, your whole machine basically. It's very difficult to do. You can basically just have this loop and a small laser, but if it's very small, maybe it doesn't have enough power to do that. So yeah, it's very tricky, but theoretically possible. And then when you are in Earth orbit and you do that, your spacecraft falls slower than the people inside. They're falling around Earth, then basically they get pressed against the ground. That's how it would work. So you could have Star Trek Enterprise level artificial gravity, but yeah, very difficult to do. And yeah, maybe it's very hard. Okay, next slide. Yeah, I like Star Trek a lot, but yeah, warp drive is not possible unless you could make the vacuum energy around the spacecraft very low. Then you could do it. But there's no way of doing that. I don't know how you could do that. Maybe no. I mean, you have to use the Casimir effect, but there's no way of having the Casimir effect everywhere around your spacecraft. Maybe by ionizing everything around you, then maybe yes. I don't know. Maybe that would polarize the vacuum in a way that would lower the density, maybe. But yeah, that's very okay. Okay, so here we have evidence from astrophysics, from cosmology. So the Earth is heavier than we think because the gravitational constant of the elements that Earth consists of are much lower than the gravity of iron. So you need more mass to achieve the same gravity as Earth has. So it's 0 point something, I forgot the exact figure. Heavier is 0.05 something, I don't know. But for the sun, it's quite significant. For the sun, it's 0.5% heavier. The sun is 0.5% heavier. It's quite significant. A black hole, neutron star and black holes, they're much heavier than we think. Their gravitational their gravitational constants are sorry. They are much lighter than we think because their gravitational constants are not. The Earth's gravitational constant is smaller, but black holes and neutron stars, their gravitational constant are much bigger because they have all these gravitational binding energy, reducing the mass but not reducing the number of particles. So they have huge amounts of gravity. So neutron stars have 15 to 20% nuclear binding, gravitational binding energy, and black holes have 30%. So they are much lighter than we think because their gravity is so enormous that they need much less gravity much less mass to achieve the same amount of gravity. So that solves the mass gap between neutron stars and black holes. They both get lighter but in different amounts, and that brings them together, and there's no mass gap anymore. So this mysterious statistical gap that you have between them, which is huge, it's like a whole solar mass or something. Yeah. So that's gone then. Not quite a whole solar mass, but close there. Okay, what's this? Yeah, you get, yeah, this is the same, just the math of it. Yeah, the mass gap shrinks down from almost 1 solar mass, 0.95 masses, to 0.3, which is the statistical gap. It's just the normal statistical gap. And you also get close to the Tolman-Oppenheimer-Volkoff limit, which is telling you what's the maximal mass of a um, when a white dwarf cannot be a white dwarf anymore, has to become a, when a star cannot become a white dwarf anymore, but has to become a neutron star. And there's a big disagreement between theory and observation, but in my theory, there's no gap size like that. And now to some more spectacular stuff, or maybe equally, but more popular stuff. I mean, everyone talks about how Einstein's theory solves the perihelion precession of Mercury. Well, my theory does it much better. For Einstein, his accuracy is like the standard to look at is like Duncombe, 1956. That's 99.89%. For me, it's 99.98%. Yeah, and overall for him, it's on the average, it's 64%, 99.60, 74, and for me, it's 99.90 for the average of all. But actually, only the last one is important because those are not such good measurements. Duncombe, it should be the same. It's funny that they have the same name. Oh well, there's a small typo. It should be Duncombe with an E at the end. I guess it's French. The E is silent. And that's where I was in 2024. But the figures I have here, I was updating my slides. The figures here are actually from 2025, because here I was using the correct distances between the planets, because when you have non-Newtonian gravity, the distance of the planets are also changing. So these results are more accurate than the ones I had in 2024. So I should write 2025 here. Next slide is the perihelion precession of all the planets. This is a big, very amazing, at least I think so, amazing breakthrough this year. Before, I didn't bother to calculate them because I thought, okay, perihelion precession in my theory should always be smaller than what we observed. But that was not the data. It was showing it sometimes bigger and sometimes smaller. And using my original method of calculation, it suggested it should always be smaller, because back then I hadn't calculated what the interplanetary distances should be. When you account for that, then you get the correct results. And I beat Einstein's theory for all the planets. You see that my accuracy is higher for all of them. And agreement, we both have agreement for all of them except for Mercury. Einstein doesn't have agreement for Mercury anymore, which is quite shocking. And it wasn't clear until 2017, because you have to really calculate for the expected theoretical prediction for Mercury. It's so sensitive. You have to calculate in all the not only all the planets, but also all the comets and everything. When you do that, you get a value that's a bit too high, and that's why Einstein's theory doesn't agree anymore. And that's something you don't notice right away, because only since 2017, Park calculated that, and it was a bit too much perihelion precession. Yeah, it was too much for me. I predict the right one. Okay, next slide. Here, many people only show the anomalous precession, so that's actually very bad. They always show only the precession that's relativistic and not the full precession. For the outer planets, for example, nobody even reported the full precession. And so they only report the anomaly, that part which is not explained by Newton's theory. So because it's so popular to show that part, I show it here too. And it also shows that the difference in the agreement is much different between my theory and Einstein's theory. So here you have 27% for Einstein, and here 73. Okay. Okay, next one. For Saturn and Jupiter, it's very hard to have data. So there's only some reportings of only the anomalous precession. which is here in minus. So so it's very hard to judge, and those come from computer simulations, which are compared then to observations, and they get adjusted all the time. So all the anomalies get adjusted away by basically rearranging all the planets, changing the distances up. It's basically just always remixing, because they always have to use computer models that are Newtonian, so they cannot deal with any anomalies. They just adjust away every anomaly. So this reported anomaly for Saturn, it got tuned down, down, down in different publications and made smaller and smaller without even explaining what happened there, why it's gone suddenly. And the one Ioria, what's his name? He's looking at he's testing basically non-Newtonian theories, and he's just saying, okay, if Newtonian gravity is not true here at this distance, then for that distance, the discrepancy should be even bigger and bigger and bigger. So he doesn't even think of theories that are composition dependent. So that's not really testing Newtonian gravity. Is not really a test. Here also test for gravitational waves, orbit decay, very famous. The Taylor pulsars, they get closer and closer because they're losing energy due to gravitational waves. If you use my theory, you can calculate that much more precise, and their calculation is not true and is not agreeing anymore since 2010. The Taylor pulsars are not agreeing with general relativity anymore, but they agree with my theory. But there's some ambiguity about them being. Are they neutron star pulsars or are they white dwarf pulsars? And in recent years, it's become more popular to think about white dwarf pulsars. So some of the pulsars can be white dwarf, some are neutron star pulsars. Okay, this is almost the last slide. One before the last slide. Okay, how many people are still there? 2 people, 3?
We still here?
I'm still here.
So
We're all still here.
Experiment, and here you have a beam, and it's basically comparing the centrifugal force induced by the rotation of the Earth with the gravity. So, but because they're on the same beam, that's why you had the different materials. They kind of they share the same gravitational acceleration, basically the same small g value, and that's the only reason why any difference at all was measured, is because one side was suspended and it was at a lower potential. And that's why you have this tiny effect, and I calculate exactly how tiny the effect is. And the odds for this experiment is 1 in 400,000 about. Yeah, and this data is from 1922, and this is what Einstein cited for his equivalence principle. And he basically ignored all those differences because they are small, but actually the error bars are not overlapping. So actually it's kind of disproving the equivalence principle. And this was not noticed until Fishbach noticed it in 86, but he framed it as the fifth force. He's the one who popularized the term fifth force. Now we have the Kepler ratios in the solar system. Kepler 1617. He basically showed that the ratio between the square of the orbit period and the cube of the distance is always a constant. But here I show that it's not a constant, and it follows the chemical composition of the planets pretty neatly. And when you use modern data, you have to actually split up the inner planets and the outer planets, because for the inner planets, they're basically using the measurement data a little bit, but then like 99% of it is just using the orbit period, and then from that getting the distance. So they're not using the real distance, but because they're using a little bit of real data in the mix, that's why you can still see the composition dependence a little bit there. Here, not so much, but we go over to these slides here. and you can see it very clearly for the outer planets. It's much more clear, and there you don't have to. For the inner planets, I had to basically magnify the zoom in on the graph basically by multiplying it with something, and that's how for Mercury it became the same. I basically multiply it by something that brings the values together for Mercury. For the outer planets, I didn't do anything. It's just the raw data. Well, on the inner planets, it's not raw data from the get-go. It's what they publish, and it's not raw data. So I just tried to extract the original pattern from the manipulated data. And then we have here Standish is very bad. P-value of over 50 means it's like negative. It's like an inverse hierarchy. And yeah, Arthur Cox also not very good, but NASA has the best one. Here you can see it follows the hierarchy pretty neatly, and the chance that this is a coincidence is 2%. So this is lower than for what was it for Kepler? For Kepler is okay. Actually, Kepler was even better. Kepler was 0.46% of it's a coincidence, and NASA it's 2.2%. Okay, that's the last slide. Yeah, that's my presentation.
That was awesome.
Very good
81
job.
slides, amazing.
Very nice. Thank you.
Listening.
Give him an applause. Come on.
Good
Uh,
call,
that's
Joe.
really good.
Absolutely.
Here,
51 slides.
audio here.
I just finished.
I'm already the second person who doesn't have audio. At least you have audio and you were able to listen to me.
Absolutely.
And everyone in the chat as well.
I'll be honest, I'm not a physicist,
don't know
but I
what
enjoyed learning as
about
much
that.
as possible.
Okay, anyway, it's a pleasure. It was a pleasure
Nice.
talking here.
Thank you.
Let me
I
check
appreciate
the
it.
chat. Okay, anyway, it's a pleasure.
Nice.
Yeah.
Are we able to?
Yeah,
Well, I
really
guess
good.
we're doing the presentation.
Okay, anyway, it's a pleasure.
Nice.
Yeah.
Are we
Big
able
applause.
to-
That was really good presentation.
Yeah, thank you for your presentation. That was awesome.
Ability, so
No,
you
he
get attracted at different speed. I mean, at different acceleration. So
Okay, so
that's
I hear you
awesome.
now, so you have to start
I've
over
got a
again.
question for you, Sky. What do you think about the? What do you think, Sky, about the vacuum catastrophe?
Yeah, I solved the vacuum catastrophe. Basically, Newton solved it. Newton solved it because Newton said in a universe that it has no center of gravity, there is no gravity. And I mean, vacuum energy is evenly dispersed everywhere, so it shouldn't have gravity. Very good question. Yeah. Yeah, if there's no center of gravity, there's no gravity. So something that is evenly distributed, only in Einstein's theory it would cause gravity. So the vacuum catastrophe depends on on Einstein's theory.
Am I
On Einstein's
correct?
cosmology.
Am I correct to say that your model gravity is more of an effect than a force, sort of thing, or is it still a force that's just dependent on the atomic, like mass density?
Well, I think we should just call things what they are computationally. I mean, in quantum theory, they say in quantum physics there are no forces. They say they're only probability distributions. Then they basically shift each other around with these gauge bosons. So there are no forces. And in Einstein's theory, it's geometrical. So they say there are no forces. It doesn't really make sense to just say there are no forces. I mean, the word force makes sense. It's in our everyday life, and I don't think it makes much sense to just say, "Oh, forces don't exist."
Fair. I like that.
Yeah, thanks.
How do you incorporate the spin vectors on the atomic scale? How does that affect, its direction, its spin? Because,
Yeah, so spin is very mysterious. You need like two revelations to have the same state, and that sort of thing that can be explained, I think, with when taking serious that particles are really these complex valued spheres. You have the real component shrink down to zero, then the imaginary component grows and it goes to negative. So it goes through all those 4 different phases, and so the rotation becomes more abstract. And I mean, complex surface spheres are basically what you use to describe spin. But for if you have bosons and not fermions, their spin is quite different, and for them also spin is more restricted. It has to always be in that direction, in perpendicular to the direction of movement for a photon. So it's quite different from an electron. It can just spin in any direction, but for okay, you can only measure it up and down, but it can be relative to any direction.
I absolutely love that. I love what you are saying right now.
So an analogy to that would be a cylinder magnet, end for end, north facing, say the roof, and it's spinning centrifugally, but it's still standing end for end. Is that correct?
Well, what I tried to finish there, I didn't quite finish, is I wanted to say that fermions would be 2-dimensional complex number spheres, so 4 dimensions, but bosons are 1 complex dimension, so it's like a 2-dimensional sphere. So that's why you have less degrees of freedom and it's more restricted.
All right. Thanks for the answer.
Welcome.
That's really cool. Awesome.
Thanks.
Philip, did you have any other questions, or? I guess for the last half hour or 40 minutes or whatever we're doing, maybe I'll just do a round table. Philip, you do, I guess, update on what you're up to. And Philip?
Phil?
You
Can you hear us?
described the annihilation process and the pair production and all that, or you agree with the mainstream?
About pair production, has anyone noticed that no experiment on Earth has ever created a surplus of matter as opposed to animate? It's always
There's delay in. I can't hear properly, but there's delay in the stream.
Oh, there's delay.
No, I hear
that's
everything.
why he was just sitting there for a minute.
No, it must be
actually, there's something. Well, in Germany it's 4:30 now. So last night I went to bed very early, and I changed my sleeping times, which are I sleep very late normally. Last night I slept very early, so I want to kind of try to sleep early. So yeah, it's 4:30, so I should go to sleep now. So I will leave you now.
Well, thank you very much for your time.
Yeah,
thanks for inviting me. It was a pleasure.
Thank you. Very good presentation.
I guess we'll just do like a round table.
I finished it up shortly before coming on here. I updated. Okay, bye-bye.
Have a good sleep.